Okay, lecture 17. Today we will cover the short channel effect by solving a two-dimensional Poisson equation. So that is continued. So if you remember correctly, so that was the magnified view of our solution domain. So what is it? Actually, this is corresponding to silicon dioxide layer, and here we have silicon. AB is related to the something like connected to highly doped source region, and here we have EF segment, and that is corresponding to the drain. So it is quite reasonable to assume that the potential of AB is determined by source and EF is determined by drain. That is quite a reasonable assumption for our calculation. So in my opinion, actually the essential point of all kinds of this complicated evaluation or model derivation is this one. This understanding the effect of AB and EF boundary. Let's say that we have a long channel device. So, or for example, let's say here we have a very long channel and consider any certain slab corresponding to a middle of our transistor. In this case, how can we determine the potential at this interface point? So the potential at this interface point, frequently called as surface potential, will be solely determined by only gate voltage. If you apply certain gate voltage, for example 1 volt, 2 volt, that determines this phi s value. But in this short channel case, actually the potential of this A point, which is still at the interface point, that is not determined by this gate voltage. So by this assumption, that is solely determined by the doping density of our source region M plus doping, and also applied source bias voltage. So that is big difference. So please think about the values you can imagine for this phi s value. So currently we are talking about the subthreshold region. So what was the condition for our subthreshold region criterion? So in that case, actually our surface potential should be much lower than 2 times of phi b. So if surface potential reaches to this 2 times phi b, we say that, oh, the channel is now inverted, so now we have a sufficient amount of electron channel. So since we are now talking about subthreshold region, so in this case we have a sufficiently low value. Then what is the typical value of this phi b? Phi b is determined by our substrate doping. So you know that is corresponding to our Na value, and at most it is around 0.5 volt. So now you can say that phi s is more or less lower than 1.0 volt in our conventional long channel case. That is the expected value of phi s. However, please think about the boundary condition for our source side. In this case, which one decides the potential? In this case, that is determined by ND, donor density in the source side, and NA. So of course this is corresponding to phi b, and you know in this case this is more or less around 0.5 volt or slightly lower, and in this case ND case, usually we apply a little bit higher doping density to this M plus region, but more or less phi at this side would be about 0.5 or slightly higher. The sum of these two numbers will give us once again the values around 1.0 volt or slightly higher. So simply speaking, think about this one. If this point is belonging to the center of our MOS channel, that of a long channel one, the value would be quite low, like just 0.5 volt, 0.6 volt, 0.7 volt. That was the expected value of our surface potential bending. But if that is connected to the source side due to the boundary condition, actually we have to have the value close to 1 volt. So that's the problem. If we just have a look at the graphs, so along the line starting from A ending at F, let's consider this AF line. Previously, our long channel case, actually we have to have a certain value corresponding to, for example, 0.5 volt, 0.6 volt, or something like that. At a given gate bias, we have a relatively low potential value. But point is, now due to the short channel geometry, A and F value at this case actually should be about 1.0 and 1.0. Of course, I would like to say, even when we consider a long channel device, this boundary condition doesn't change. It means that instead of this relatively short channel device, consider a long channel device A and F. Let's say now we have a very long channel, and also in this case we must have the value relatively low. However, even for this long channel device, at A point our potential should be 1.0 volt, and F point, if we just apply 0 drain voltage, then that should be 1.0. What's the problem? The problem is, now in this case, well, we will have a certain transition from this 1.0 corresponding to the source potential or drain potential to surface potential of our long channel device. There will be a certain length scale for transition from 1.0 to 5S. And here also we have a certain transition region from 1.0. 1.0 means that the value dictated by our drain and to the surface potential value. That length scale will be found here. Okay, that was the point. However, if we reduce the length of entire channel, then now we will have a certain length scale, and the effect of this transition region cannot be neglected any further. So that's the reason why, of course, if we just observe at the center of this device, then still, well, it's not that much affected in this scale. But if we make an even further reduced case, A and F, in this case, actually their two transition regions are overlapped to each other. It means that the value raised by this source and drain potential really affects to entire channel region. That's the reason why even this potential barrier seen by our electrons can be affected by this boundary condition. That is the problem. So please note that although we consider different boundaries, actually we have 4 different boundaries. One is AB boundary connected to the source, and EF boundary connected to drain. And also we have a lower one connected to the substrate contact, and top one corresponding to the gate one. but gate is just shared by all case, so that doesn't matter. So we have three other sides, but point is important one is this AB and EF1. If we consider just a long channel device, it's just okay. But if we consider short channel device, then our condition for this AB and this EF segments are much less than our nominal value at the center point. So that really increase entire potential. That's the point. Okay, so let's go to our entire solution procedure. Up to now, I just explained the importance of AB segment and EF segment, and now let's think about this one: AB segment and EF segment, and that is corresponding to the doping dependent one, which is quite high, close to 1 volt, and plus we have additionally we have VDS dependence in the case of drain case, because drain is usually highly biased, not like 0 and 0, but let's just say, for example, we apply 1 volt, then of course, so this is drain side potential penetration will be more severe than this source side, so we must consider this one also. And top boundary condition is not affected by this channel geometry, whether that is short or whether that is long, that doesn't change the value. And along CD line, yes, we just say that if we say CD is located here, then it means that actually the maximum depletion is given as this way. In between this B and C and D and E, we say this is depleted and depleted. And at the end of our previous lecture, we have made a short discussion about how can we determine the length of BC and length of DE. But as I told you before, that is just made a quite a crude approximation. We just assume one-dimensional depletion approximation and just rotate it to, so rotate it from this vertical way. Say this is the depletion width for source side, and this is just copied to the BC. And here also we may have the depletion width for drain side that is copied to the length of DE side. So that doesn't matter actually, that because we are now talking about the change of our potential mainly due to the drain voltage. So that is not that much affecting our final result. Okay. So anyway, that is the one. In my opinion, from now on, we'll see tons of equations, but before talking about equation, please try to understand the essential part of this modeling. The essential part of this modeling is due to the raised potential given by source and drain region. So our entire channel potential should be raised. So that lays under given gate voltage. So although gate voltage is fixed, but due to the action of AB and EF side, our entire potential is now raised. So it is interpreted as reduction of threshold voltage. So although we didn't apply any further gate voltage, now the channel becomes a little bit easier to overcome. So now we say that that is the reduction or role of our threshold voltage. Okay. So now the solution procedure is quite standard and typical. So now we have, simply speaking, now we have 4 sides, and 4 sides we have all directly boundary condition. So let's just remember, for top we have the boundary condition corresponding to the gate voltage, and bottom that is corresponding to the something. So body one, body potential, and also here we have some part is corresponding to the source potential, and some part is corresponding to the drain potential. But anyway, their values are assumed, so there is no ambiguity in this side. And how about this source side? That is fixed, and also that is fixed. Now think about this case. We have a rectangle domain, and in this rectangle domain, the equation we must solve is just simple, also not exactly this way, minus epsilon. So we must solve this simple Poisson equation, and here, all four sides or all four boundaries we have directly boundary condition. Then how can you solve this boundary condition? Even better thing is, if rho, this is net charge density, if that is a function of a potential once again, then we must solve a non-linear equation. But fortunately, since we have neglected contribution from electrons and contribution from holes, now this rho, the net charge density, is a given number. Inside this silicon system, that is just Na. Inside this oxide system, it's just vanishing. So now there is no non-linearity in this case. So let me just say, we must solve linear Poisson equation. Oh, linear Poisson equation easy to solve, plus all four boundary conditions. So that is given as a Dirichlet boundary condition. By combining these two conditions, actually we can try to solve this system quite easily. Since this is linear, so now we can just decompose our entire solution, the total solution, into several pieces following different boundary conditions. For example, let's say, so although it is not, please, although it is not directly equal to our case, please think about this one. Let's say this left side is 1 volt and right side is 2 volt, and entire bottom is just 0 volt, and happen to be the top is biased to 5 volt. And now we must solve just a simple Laplacian equation. Then how can we solve this problem? If we must solve this problem, what we can do is, yes, for example, 5, 0, 0, 0. For this case, just to solve one Laplace equation, and also solve 1, 0, 0, 0. For this boundary condition, please try to solve once again. And also you can say, you know what I'm doing right now. So also you can say 2 volt and solve the Laplace equation. By solving these Laplace equations 3 times with only different boundary conditions, what you will get is, now you have phi 1, phi 2, and phi 3, and since all of them are just linear, so that is important. So since they are linear, by adding them up, phi 1, phi 2, and phi 3, that will give us the original solution for the original problem. Okay, so simply speaking, we can just decompose our equations into several pieces. So now you can have the solution. Quite similarly, we will try to do this job. Okay, here we have 4 different functions calculated by solving Laplace equation or Poisson equation, but with different boundary conditions. So what we wanted to do right now is like this. Here we have the conditions. Yes. Now this part is corresponding to the gate, and this part is corresponding to the body potential, but body potential is just grounded, so that's not important. And here we have a source potential and drain potential. So what we wanted to do is at the first time, well, why don't you just do in this way? First consider gate 1 and solve source 1, drain 1. Looks quite reasonable, but point is there is one thing. This is not a Laplace equation. We must solve the Poisson equation. So here we have a non-zero component here. Then which one should take this non-zero component? One possibility is, okay, just to make a 4 times division, so each equation takes equally. However, please note that the best way we make this decomposition is when we make extremely long case corresponding to long channel limit, then our solution should be corresponding to the long channel case. So are you with me? Right now we are considering a short channel case, so therefore aspect ratio is quite close to 1:1 or 1:2. However, if this solution procedure is reasonable enough, then our formulation should be valid not only for this 1:1 or 1:2 case, but we must have a valid expression for quite wide simulation domain, solution domain. So in this case, actually impact of this source side and drain side, that doesn't matter. Only important one should be gate related one. So right now we can understand, although we have 4 different boundaries and wanted to solve 4 different times this partial differential equations, but most important one is the one corresponding to the gate side. Gate side should take the long channel model, and once after this long channel model is taken by this gate potential model, after that the remaining part will be considered by this source and drain. So what does it mean? Simply speaking, I'm not trying to solve in this way. This is not a good way to do. Means that, let's say this is 0 and this is 0 and gate voltage is given by gate voltage. Then please try to solve it. In this case, since this 0 volt and 0 volt is not corresponding to the long channel solution, certainly we will have a position dependent. Position dependent means that this y directional dependent quantity. At the end, at the center of this system, of course, our potential will follow that of a one-dimensional MOS case. However, if we go to this source side or drain side, that will be affected by this 0 volt or 0 volt case. So main idea is not solving this just mechanical decomposition into 4 different parts, understanding the importance of gate dominant one. So instead of this one, we introduce the boundary condition like this. The boundary condition along this AB line and EF line just follows that of MOS equation. So that is my point. So please have a look at. That is, in this notation, we just use alphabet V to denote the solution related with gate voltage, and in this case, this one takes all. Poisson equation is solved. Poisson equation means that now we have a non-zero doping density inside our system that is considered by our Poisson equation, and upper boundary condition, this upper boundary condition is corresponding to VGS related one. So just to consider long channel part, after that only difference from this long channel approximation is considered in this left side and right side. So let me just repeat once again. If we adopt this kind of approximation, so let me just do it together with you. So say we have certain gate potential. So due to the boundary condition, now we have VGS minus flat band. That is the value required for this point. And let's say that here we have value phi equal to 0 due to the definition of our potential. And now let's say we have a certain thickness corresponding to oxide thickness, or actually in this case, in order to compensate the difference between permittivity between silicon and silicon dioxide, we introduce 3 times of silicon dioxide thickness. But anyway, now let me just draw the solution. In this case, we will have just a straight line corresponding to the potential deviation inside the oxide layer, and also we will have parabolic increase of our potential. So here we have a parabolic behavior because this is in this entire layer is corresponding to the depletion layer. So now we have NA everywhere, and once after we meet this point, now we will have certain smooth curve. So maybe you can ask me this question: why you don't introduce discontinuity in these 2 parts, one part and other part? Usually, if we are considering the usual MOS system, then we must introduce discontinuity. So let me just do it together with you. Let's say this is a phi and this is a 0, and usually what we do is here minus T ox, and let's say this is a depletion width. Well, in usual case, we have a parabolic behavior, and this parabolic behavior is corresponding to the depletion layer, and eventually we will have a certain electric field. So this is corresponding to the silicon side electric field. And if we have a silicon side electric field, what should we do? If we have to draw the potential profile inside the oxide layer, we must have 3 times higher electric field compared to the silicon side, because permittivity of these 2 regions are different. So if this is the 1, then we must have 3 times higher electric field. However, please have a look at my new drawing here, shown here. In this case, I intentionally introduce 3 times thicker oxide layer, and instead we just assume that the slope shown here is continuous. So intentionally length is increased, and permittivity is just to match to that of silicon dioxide. So then anyway, let's come back to our original discussion. This is the solution for our V case. So this is the potential obtained from our top side equation, and although it is written as x comma y, in general it has a y dependence. However, actually, since this is the solution of our MOS equation, whether that is corresponding to y equal to 0 or whether that is corresponding to y equal to L, that doesn't matter. We will just have same value everywhere. It means that even when y equal to 0, we will have a potential looks just like this. That will be the potential drawn at y equal to 0 side. Then please estimate the value at this point. What will be the value? Of course, this surface potential will depend on your gate voltage, but its value would be about 0.67 or something like that, which is far lower than the the 2 phi b value. Now, as I told you and as I emphasized several times, when we draw once again the boundary value, now it says 1.0 volt, or in this notation corresponding to phi bi, built-in potential between our M plus source region and substrate. So that is much much higher than our surface potential. So now you have the mismatch between your required boundary condition and the boundary value obtained by your V. So now it means that this amount of a potential value is not satisfied by our V value. Okay, so by considering only V, the value determined by our top gate potential, then now the boundary condition for this top surface is completely satisfied. Oh, we are happy. And by using the homogeneity of our V sub V comma V x over x and y, now we have a mismatch in our solution. Although we have a well-defined boundary condition, but that is not corresponding to our solution V. Actually, this remaining potential difference that is used for our next function that is called as u sub L. Now this u sub L function just matches the boundary missing boundary condition in the left boundary, and for all other 3 boundaries it just say everything should be 0. So are you with me? Simply speaking, if I have to draw once again this diagram once again for our u sub L for left boundary, now for this left part, the boundary value will be phi the boundary condition minus V, and otherwise for top 0, right one 0, and also bottom one we will have 0. Then by combining these two, V and U sub L, then what will happen? So if we adopt this kind of combined solution, then we will be quite happy with this top side and left side, but unfortunately still we have disagreement on our right side. So that mismatch will be, of course, as you may expect, by introducing another solution called the U sub L, which just matches the difference between required phi and all other values like U. That will be used the boundary condition. So simply speaking, this value will have a positive value. Please think about this U y equal to L case once again. We will have just a copy and pasted version of our potential. Yes, that will be our potential value at our y equal to L case, and also the required bias value will be even higher. That value will be given by phi bi plus drain source voltage. If we apply 1 volt to our drain or 2 volt to our drain, then we will have even higher disagreement between our blue curve, the one obtained by V function, and our drain side potential. So now that is the overall solution. The reason why I'm spending quite a long time about explaining this one is you must understand the problem setting and to understand the solution procedure, to understand what is inside it. So simply speaking, starting from our long channel approximation, long channel MOS case, not considering drain bias, after that, impact of this left side and right side are included by U sub L, U sub R functions. And yes, even when we have zero drain bias, please note that our U sub L makes a quite significant impact when we have a short channel device, because even when drain bias equal to 0, but still our phi and V, they are different, and usually this value is always positive in our case. So that's the reason why we have this kind of condition. So now let's go to this one. Well, then where can you find the V, actually, which is given as just a vertical position dependent quantity? We spent several lecture hours to discuss V. So once we have depletion width, and starting from this depletion width, we have a parabolic behavior, potential behavior, and that is corresponding to our NA value. So this is nothing but just a parabolic value. Now we know V of X quite well, so that's the reason why in this slide we start from U sub R. So I think that okay, it's okay. So U sub R means that this the function corresponding to this side is a U sub L, but now I'm talking about U sub R, which is corresponding to the drain related one. So please have a look at this one. Since this function is only corresponding to the drain side, in the source side it is set to be 0, and for gate also it is set to be 0. Why we set to be 0? Because the impact of our gate potential is already considered by our V function, so we don't have to consider it any further. And now bottom one, it's okay. So now only non-zero side is the right side, and this one just given as the boundary condition minus our previous solution. And please note that once again, this previous solution is just corresponding to the potential distribution of a defletion layer inside the silicon side. So, but boundary condition is a constant inside the silicon region due to phi bi plus our drain voltage. So if we apply high drain voltage, actually this value can be quite high. So please note that this is about 1 volt, but depending on your bias condition, if you apply 2 volt, then this value can be even about 3 volt, 4 volt. You can easily increase this number quite easily. So now, well, now this is given as simple. So overall, now along this line 0, also along this line 0, and also along this line everything is just 0, and we have only one side which does not vanish. So maybe you have solved this similar problem in your electrostatic case, so in your sophomore level electromagnetics or not, but anyway we can try to solve this one with quite simple expression. I'm not saying that this is simple, but although we have summation and coefficient and normalization, but basically this function is just a product of these two different functions. One is corresponding to hyperbolic sine along y direction, and another one is a sine function along x direction. That's it. Sine function or hyperbolic sine function vanishes at a 0 argument. So simply speaking, if we follow it this way, y equal to 0, then what happens? Hyperbolic sine functions vanishes. So hyperbolic sine vanishes always. So that's the reason why our boundary condition, this boundary condition is well satisfied by this test function, product between hyperbolic sine and sine. And how about this top and bottom boundary condition? If we apply the top surface, at the top surface we assume that the position is minus 3 times the oxide thickness. Minus is understood because this interface is regarded as x equal to 0. But why we have number 3? It is because in order to compensate the difference between permittivity. So if we insert this minus 3 times Tox into our argument, then you can see that the overall argument of our sine function becomes 0. So sine 0 will give you once again 0. So our UR function just vanishes at this top surface. And how about this bottom surface? Bottom surface is given as x equal to, well, I don't know, let's say that maximum depletion width, and let's say that x equal to maximum depletion width. And when we insert it instead of this one, x equal to maximum depletion width, then on top of it we have maximum depletion width plus 3 times T ox. That is normalized by lambda. Then what is the definition of lambda? Actually, the lambda is defined as WDM plus 3 times T ox. So this one becomes just number 1, unity. So simply speaking, in this case we will have sine times n pi. Of course, n is an integer. What does it mean? Sine, when its argument is integer multiple of pi, it becomes also always 0. So by construction of this test function, on this bottom side, of course, also we have a function vanishes everywhere, regardless the value of our mode n. If this mode is n equal to 1, now we say that along x direction this is just a half period. This is a top surface and bottom surface, and when n equal to 2, it means that now we have a full period along. This is minus 3 times T ox, and this is WDM. And if we go to even higher values like n equals 3, 4, 5, then we can have more and more half cycles inside it. But anyway, we can understand, regardless the value of n value, that will give us the correct boundary condition. And the only non-vanishing value is corresponding to this one. Yes, when we insert sine, hyperbolic sine, and n pi L over lambda, of course this one does not vanish. So that's the reason why we can say this part we don't have vanishing UR function. So now you understand, at least following my discussion, now you understand this basis just to satisfy, how can I say, the boundary conditions for top, bottom, and left one. At least at those 3 boundaries, the function vanishes. However, please note that actually this function should be a solution of a Laplace equation. Also, how can we verify this is the solution of the Laplace equation? In order to match this Laplace equation, actually we must take the partial derivative with respect to x and partial derivative with respect to y, second derivatives. Then fortunately, this is hyperbolic sine, when takes twice the derivative, it will give us the coefficient corresponding to positive n pi over L square. That is given as this one. So let me just do it together with you. If we have a sine hyperbolic sine kx, and if it is derivative taken twice, then it will give us just squared k and its original form. And if we go to, instead of this hyperbolic sine, let's say we have just a sine function, then what happens? in the case of a sine function, when you take the differentiation twice, then you will have minus square k. Are you with me? I mean that if you have sine kx, then it becomes minus k square sine kx. It just recover to itself with an eigenvalue corresponding to minus k square. And in the case of a sine hyperbolic function, it just come back to itself, hyperbolic sine, however, positive with a coefficient positive k square. So simply speaking, what I wanted to say is, when we have u sub r, when we take it along y directional one, then it will generate minus, positive k square u r. And when we take the partial derivative, second order partial derivative with respect to x, it will give us minus k square u r. And when they are summed up, then this positive k square and minus k square are cancelling each other. So we will have just taking the Laplacian of this test function will give us just number 0. What is it? Actually, this test function just satisfies the Laplace equation. So that's the reason why we can try this UR. Although it looks quite complicated, having mode summation and coefficient for each mode, but this is just a disguised form. Essentially, there are only two factors: hyperbolic sine along y direction, channel direction, and sine function along x direction. And since hyperbolic sine and sine itself behaves differently with respect to second order derivative, that's the reason why they can be a harmonic function. Harmonic function means that the solution of a Laplace equation. And now we can just match the number like n to describe the boundary condition. That's it. So by changing n value and finding out the corresponding coefficient to c sub n, then we can match the right boundary condition. Then once we match the right boundary condition, top, bottom, left, all of these three parts are already matched. And also Laplace equation itself is matched or satisfied due to its construction. So now it becomes the complete solution of our equation. Okay. Well, so if you cannot understand it right now, then please have your own study on this one. But I said this is not, although it takes a long time to explain it, but actually it's not that difficult. Once you think by yourself, you can easily get the solution. So point is, now we must do the decomposition of our boundary values into this C function, a C coefficient. Simply speaking, we must take this Fourier series expansion. But please have a look at this one. Now we have 3 times T ox thickness, and now we have WDM. And relatively short distance, and here we have relatively thick values for our depletion width. And once again, let me just draw once again the potential. And the potential is drawn as a parabolic function, and our boundary condition is just given as a fixed value. Then please try to estimate how does the difference between boundary potential and our solution V. So let me just repeat once again. This blue line is corresponding to our V function, and this green line is corresponding to our phi function. And when we draw our difference between phi and V, please try to draw it. Then maybe you can easily understand in this interface side that is relatively small because the surface potential is increasing, and in this case this is a full solution, and we will have, this is the new boundary condition for our U sub R. Now U sub R looks like this. This is the U sub R, and please try to guess what will be the most significant mode. Please, I mean that if we consider just the lowest mode n equal to 1, then how does it looking? So let me just draw. If we just follow the n equal to 1 case, so if we consider n equal to 1 mode, it just looks like half sign, all positive. So we just make the summation or integration of this black curve with this yellow curve. So maybe you can understand they will contribute to a positive number. Please think about n equal to number 2. Then we have to make an integration of this black curve for this full sine curve. If this is corresponding to full sine curve, actually this part will contribute positively, but for this part it will contribute negatively. So they are cancelling to each other. So what I want to say is, although here we have expansion corresponding to C sub n, of course n equal to 1, 2, 3, 4, when you go to n equal to or even higher value, actually with higher n value, this sine function fluctuating quite rapidly. So now think about, for example, n equal to 100, then how does it look like? Then we will have 50 cycles inside this system. And please try to integration. What will be our result? Within quite a short time, although integrand doesn't change, but we are just taking sine function. So that cancel to each other. This up and down cancel, up and down cancel. So simply speaking, this black curve or the boundary condition for U sub R is a slowly varying function. So higher order coefficient doesn't contribute to our solution. So only important one, the most important one is just n equal to 1, the lowest mode, just corresponding to quite close to the average value of this unmatched boundary condition. So that's the reason why in the next part we just keep only the C1 coefficient. In general, of course, we must consider C2, C3, C4, blah, blah, blah. But if we go to higher mode, then actually their actual value decrease quite rapidly. So we can just keep the lowest one, C sub 1, and of course B sub 1 is corresponding to U sub L function, then now we can find out a simple form as shown here. Please, once again, this function is corresponding to our V sub x. This is a long channel MOS equation, and now we have the dependence on source potential and dependence on drain potential. They are reflected in this way. Then how can you actually, you can ask me this question, okay, now previously I had VDS equal to 0. Now we have a certain B1 and C1 coefficient, and I intentionally increase this value, VDS value, to 1 volt. What happens to my calculation procedure? The answer is, since you have increased your VDS value, this C1 value is affected by this new VDS value. Your B1 value doesn't change at all because it is affected by your source voltage, and source voltage is kept as the same. So now you have a new expression, although it looks a little bit complicated, but please note that once again, this is long channel MOS, not MOSFET, but MOS capacitor, and impact of source side is corresponding to this B1 function, and C1 is corresponding to the drain, and of course we have a mixing term. What is it? That is corresponding to the body part, substrate part, but that is not included in this case, because more or less we are interested with the potential at x equal to 0, the surface potential, and that surface potential is not that much affected by this substrate condition, so we just neglect it. Okay, so, and here you can see that the textbook says that approximate value for B1 and C1 is given as this way. Here, as I told you before, phi BI, that is around 1 volt, and phi S, it really depends on your gate voltage. If you increase gate voltage, then this phi S value will increase, and yes. So, but anyway, this phi S value itself is lower than 1 volt. And you know that A coefficient, this is another coefficient, but it is known to be about 0.4. So simply speaking, how can we understand the amplitude of this B1 coefficient? Even when you have 1, but this is corresponding to about 0.6, and you know 4 over pi, that is close to just number 1. So simply speaking, our B1 value is about 0 point something positive. So that's the reason why now you understand, due to the action of this B1, our potential will be raised compared with this long channel MOS case. Even when we have zero drain bias, but still, due to the existence of a source, our channel will be affected. But point is, its effect is locally limited. Please have a look at here. B1, C1, this one. It has certain exponential behavior, and now you can understand if we draw y-axis and impact of this B1 or C1, they are just exponentially decaying with a certain length scale of lambda. And also, in this case, its effect is decaying also with length scale of lambda. Although it is written as a sine hyperbolic, actually what is the sine hyperbolic? Sine hyperbolic x means that by definition it's nothing but exponential x minus exponential minus x divided by number 2. So if we have a positive argument, actually this second term just vanishes. It is just a half of exponential function. So also, so therefore we can understand actually this lambda is the length scale for impact of our drain potential or source potential beyond several lambda, then it doesn't make any impact on our potential. That's the key point. Please remember that lambda is the length scale, and this lambda is by definition it was given as 3 times Tox plus WDM. So this is depletion width, and this is 3 times Tox. Why we have 3 times Tox? This number 3 is obtained from the ratio between silicon permittivity and oxide permittivity. So this is a given system. So anyway, this is the length scale. If we can reduce this lambda down, if we can have a quite a short lambda, it means that for given length scale 0 to L, if our lambda is short, then yes, its effect will be quite much limited to source and drain side. But if we have a relatively longer lambda, then what will happen? We will have this behavior. So our usual goal to have good scalability is have the shortest lambda scale. Then how can we have a shortest lambda scale? So of course the depletion width should be reduced. Then how can you control depletion width? Depletion width is a function of doping density. If we have introduced higher doping density, then we will have a relatively short depletion width. So by increasing the doping density, we can have a relatively short depletion width, and it gives us some chances to scale our technology down. So please understand this is a quite important message. So now let's go to this one. Now although that is, I'm not saying that this phi x comma y, this is the exact solution. Of course, this is not the exact solution. Our problem itself, this problem itself is not very accurate. And our solution is also kind of a truncated solution. Although we must perform the series expansion, we took the lowest order expansion, C1, B1 expansion. So therefore, this is not very accurate, but it contains very important information. So for example, taking just x equal to 0, what is x equal to 0? This is a silicon dioxide interface. Now we can have the profile along y direction. So we have, as you can see here, now you have a exponentially decaying impact of B1, and also we can have exponentially decaying impact of C1. Okay. So now, well, I think that finishing this discussion in today's lecture is too ambitious. So let's just review our discussion up to now. So, well, so today I have spent quite a long time to tell you about the two-dimensional Poisson equation. So actually, in our previous lecture, I just introduced the equation itself, and in today's lecture, we have introduced some techniques to solve this problem, and it was quite easy. It means that long channel MOS, that should be the key. First, V of x takes this long channel MOS equation. After that, due to source potential and drain potential, we have the mismatched boundary condition. That is covered by our UL function and UR function. Then how can we match these boundary conditions? And by applying the series expression like B1, B2, B3, by using them, we can match the source potential and also C1, C2, C3. By them, we can match the drain potential. But as I told you before, the shape of our boundary condition just looks like this, slowly varying function, boundary condition. So higher order expansion doesn't make any big impact to our coefficient. So we are allowed to just lowest order one. So that's the reason why in this approximate solution, we just took B1 and C1 value. Of course, if you wanted to do it even better, then we can apply B1, B2, or even higher component. But anyway, that was the solution. So at interface, we can find this simplified form, and later we will try to find out the minimum potential by so let me just try to draw it, this equation. So this is y, and y equal to 0, and here we have an endpoint of L equal y equal to L. Please test three different positions: y equal to 0, y equal to L, and y equal to half of L. This is of course the midpoint, and in this case we wanted to have a vanishing function. So when we have y equal to 0, then what happens? When y equal to 0, then this y equal to 0, C1 coefficient doesn't play any role. Okay, so that vanishes. And how about this? In this case, when y equal to 0, this becomes a 0, and we have a hyperbolic sign of pi L divided by L, but the same factor can be found here, so they all vanishes to cancel out. So what we will get is just phi s plus b1 for this entire system. After that, of course, we have a sine pi 3 times t ox lambda. So we will have a certain value higher than phi s value. This difference is corresponding to b1 sine something. And please go to this y equal to L case. In this y equal to L case, actually b1 doesn't contribute any further, and y equal to L, this c1 contribution is cancelled out, this lower part. So we will have simply the values c1 sine pi 3 tox lambda. We will have this value. And for other parts, we can expect exponential decay of this information from B1, and also exponential decay from the impact of C1, and inside it, so the value will be just given as phi s. This is the expected behavior of our surface potential. So right now, I have drawn the length scale L, which is much longer than our length scale lambda. So that's the reason why we have the intermediate point, which behaves just like a long channel device. But now, let's say instead of this long channel, think about a certain L value, which is quite short, like this. Then what will happen? This one will give us exponential decay. Also, this one will give us exponential decay. By summing them all, eventually we will have the function just looks like this, and that is much higher than long channel counterpart. So that is actually the increase of minimum potential, and that is also interpreted as reduction of our threshold voltage. Even without paying the additional gate voltage, now we can see the reduction of a potential barrier that is interpreted as a threshold voltage roll up. Okay, sorry for this delayed lecture progress, but I think that today's lecture is quite important. So, okay, so we will continue our discussion on this Wednesday. Thank you.